All right, here we go. Unit 5, Lesson 3, the quadratic formula, Day 3. Going to do a brief walkthrough of the increasing levels of difficulty we've worked with the quadratic formula, and finally take it to its final level, which is also going to introduce us to a new concept, the concept of imaginary numbers and complex numbers. So, as a quick refresher, right, quadratic formula, if you are given an equation in the form 0 equals some number times x squared plus some number times x plus some number c, quadratic formula can be used to find solutions. Where that's really important is if you just have a general f of x function graphed, so f of x is some quadratic function, it tells you where the zeros are. It tells you what values of x make f of x 0, or where the 0/x intercepts to your solutions will be. Now in class, I briefly touched on this term. This term right here, for what is under the radical, what is under the square root symbol, it is known as the discriminant, and it's the most important part of the quadratic formula. And the reason for that is it's going to determine how many and what type of solutions we have. So let's do a quick overview of what we've seen so far. Types of discriminants. First case, right, we've seen positive discriminants. So here's a quadratic formula problem, 4p squared minus 4p minus 15. Not going to go through all of this, right? We've been through a number of these quadratic formula problems. A is 4, B is negative 4, C is negative 15. You plug into the quadratic formula, and what you would find here is a positive number, right? 256 is greater than 0. It's a positive number. What that means is, now in this case it's a perfect square, but not always. Since the square root of 256 is 16, because it's 16 times 16, you're going to have one solution that is plus 16 over 8. We work that one out, and that one ends up being 5 over 2, or 2.5. And we have another solution from the minus 16 part. We work that through, and we get negative 3 over 2, or negative 1.5. And so the key idea here is, if what is under the square root, right, if that 256 part is a positive number, well then your quadratic is going to have two zeros, two solutions where it is equal to 0, because you're going to have plus that square root and minus that square root. Now, that was a case where we get a perfect square in the radical. That's perfectly fine if it's not a perfect square in the radical too. You'll still have two solutions. So here's an example where the discriminant works out to be 12, right? And 12 is greater than 0, so therefore we'll have two solutions. And we work this out. We can take out a 4, right? Because the square root of 12 is the square root of 4 times 3. That 4 comes out as the 2 for 2 root 3. And so what we have here when we simplify this fraction is negative 4 plus or minus 1 root 3. Now, the square root of 3, it's what we call an irrational number. It can't be converted into any sort of a over b fraction. It's a decimal that goes on forever. But these are real numbers, right? And if you work it out on your calculator, you can get approximations. And there are those two solutions, right? So what we have here, notice negative 4 is in the middle. And then we're going to have plus the square root of 3 and minus the square root of 3, right, to get us to those two zeros. So same idea, even if it's not a perfect square. The last one, right, and we didn't really talk about this a lot in class, but it did come up in the delta math sometimes, and this is sort of a funky special case. If your discriminant works out to be 0, what that will mean is there will be one solution, right? And the reason for that is the square root of 0 is 0. It doesn't matter whether you add or subtract 0. You're still going to get 8 over 2 in both ways. And so sort of graphically what this would mean is it would mean you just barely exactly touch the x-axis at x equals 4, and then the quadratic starts to head back up or head back down depending on which way it's opening. So we've done two cases so far. If the discriminant, if what's under the square root is positive, two solutions. 0, one solution. What about negative discriminants. And this is where things get weird, okay? And so before I sort of reveal this graph here, I want to just think about it. So we got another quadratic equation, you work it out, yada, yada. And what we wind up here is negative 16. And so let's think about that for a second. The square root of negative 16. What could that possibly be? Well, 4 times 4 is positive 16, so it's not 4. And so a lot of people will jump to it immediately. They'll say negative 4, but think about that for a second. Negative 4 times negative 4, a negative times a negative, is also a positive 16. So that doesn't work out, right? The square root of negative 16 is not negative 4. It turns out there are no real solutions to the square root of negative 16. There are no real numbers that multiplied by themselves make 16. And so graphically, this quadratic function has no real zeros. It never touches the x-axis, right? The closest we get there is x equals 4, but it never, or x equals 3, y equals 4. It never touches the x-axis. It has no real zeros. This is where things are going to get weird, right? And this is where we're going to introduce this idea of complex numbers or complex solutions. This is going to be a little bit tricky here for a moment. Complex numbers have a real part and an imaginary part. So let's talk about imaginary numbers. Going to do a brief intro of that today, and that'll be what the focus of is of today. So here we go. Imaginary numbers. This is a completely new concept here. Basically, there are situations, right? A lot of like electrical engineering and other like advanced mathematical concepts where it can be useful to have temporary solutions. It can be useful to have solutions to things like x squared minus 6x plus 13 equals 0. We just showed, right, this is this same blue graph, there are no real solutions here. There are no places on the real number line where x squared minus 6x plus 13 is equal to 0. But it can be useful to have quote-unquote solutions to it. So mathematicians invented this concept called imaginary numbers. So the basic unit of the imaginary number is I. Okay? And you're going to see it written as a cursive I, maybe like that. I can't really do the keyboard version, but I like to write it when I write it out like that, like I. And you should too. Now what I is defined, the definition of the number I, and it's a number, it's just an imaginary number, I squared is equal to -1. That is how we define I, is by saying that I squared is -1, right? And that should show you why it's imaginary, because there are no real numbers that times themselves are -1. There's no real number that times itself is a negative. And so the implication there, if you took the square root of both sides, so you take the square root of I squared, you get I is equal to the square root of -1. And the reason it will be useful is that we can now take square roots of negative numbers. We can now take the square roots of negative numbers. So let's think back. Let's see how it's useful here. If we have the square root of -16, there's two ways to think about this, right? Some people are going to like one way, some people are going to like the other. If I have the square root of -16, well, one way I could break that up is it's the square root of -1 times the square root of 16. Right? We could have said this yesterday. And then we could have combined these things back together, and we could have said, okay, the square root of 16 is 4, and I can't do anything with that square root of -1, so I'd leave it as the square root of -1. But we now know I is the square root of -1. So if we use our imaginary number I, we can turn that into I, we can turn that into 4. Another way of writing this is 4I. Now some people, myself included, prefer this method of thinking about it. We could take 16 and turn it into 16 times I squared on the inside, because I squared is -1. So -16, 16I squared, the same thing. And then, see, the square root of 16 is 4. The square root of I squared is I, 4I. So two different ways of thinking about this. The square root of negative 16, its imaginary number is called 4I. So two more quick examples, right? If we had the square root of negative 40, one way to think about this would be the square root of I squared, right? I like to just do that at the beginning. I turn that negative into an I squared, and then 40 is 4 times 10. And so I think about what's going to come out here. I squared comes out as I. The square root of 4 is 2. And there's nothing we can do with the square root of 10. Now, conventionally, the way we write this is the number first, then I, then whatever is left over in the radical. So this would be 2I times the square root of 10. I'll show this one the other way in case you prefer it. The square root of 54. Well, that's the square root of negative 1 times the square root of, I think this is going to be 9 times 6. Yep, the square root of 9 times the square root of 6, right? So all of those things multiplied together are negative 54. But what we know is that the square root of negative 1 is I. The square root of 9 is 3. And the square root of 6, there's nothing we can do here. So we have I times 3 times square root of 6. We would have what we call 3I root 6 conventionally, right? And just a quick detour, right? One way to kind of combine these approaches just to remind yourself why this works. Negative 1 is I squared. The square root of I squared is I, right? That's where that's all coming from. And so let's just, as a final couple today, let me just finish off, right? This is where we left that last problem. We left that last problem saying 6 plus or minus the square root of negative 16 over 2. Well, I learned here that the square root of negative 16, right? Square root of negative 16 is 4I, right? Another way to think about this, if you took 4I and you squared it, you get 16I squared equals negative 16, right? That's another way to think about this. So we have 6 plus or minus 4I over 2. 1, 2, 3, all three of those terms can be divided by 2. So we'd have 3 plus 2I over 1, or just 3 plus 2I would be our finale there. Okay? So one last one, just so you can see it worked out all the way from the beginning. Let's take this problem here, and this is exactly what it's going to look like on Delta Math. So if we have our quadratic, I'll try and get through this one fairly quickly here. Like 15 minutes is about the max video attention span that I think we have. So if you've been tuned out here, try to push through, stay with me for this very last example. Make sure you understand what's going on. So if we do our quadratic formula, negative, let me do this like this, we'd have negative b plus or minus the square root of b squared minus 4ac all over 2a, and we go ahead and we plug these things in. Negative b plus or minus b squared minus 4 times a times c. Oh man, I picked a fun one, didn't I? All right, all over 2 times a. And so when I'm doing this problem, right, this will actually be useful, like, where do I say, okay, that's not worth doing by hand, I'm going to do this in the calculator, right? What I'm going to do in the calculator is I'm going to do just the discriminant part. So I'm going to have 32 plus or minus the square root of, now notice I'm just going to put this all in parentheses, negative 32 squared minus 4 times 67. There we go. So we get negative 48. Seems reasonable, right? It wouldn't have seemed reasonable yesterday, but now it does. All over 8. Okay, thank you, Desmos. I got it from here. So we got 32 plus or minus the square root of negative 48 over 8. All right, final warning, right? Like, this is the last place. If you're still kind of zooming out, right, this is what's actually different about today. Negative 48, and I like to do this somewhere else in my paper. Negative 48, well, I can think about that as like the square root of negative 1 times, let's say, ooh, I found it. I found the fastest way, but I'll do the slowest way. The fastest way would be 16 times 3, but let's do the slow way for fun. Let's say this is the square root of 4 times the square root of 12. So the square root of negative 1 is I, the square root of 4 is 2, and we don't know yet what to do with the square root of 12, so we'll have 2i times the square root of 12, But the problem is here, the square root of 12 can also be further broken up into the square root of 4 times the square root of 3. So we have 2i times the square root of 4 times the square root of 3, 2i times 2 times the square root of 3, 4i root 3, right? And so, woo, that's a lot of writing. Let me just show you really quickly how I would have done that really quickly. I would have said, okay, negative 48, that's I squared times 16 times 3. I squared comes out as I, 16 comes out as 4, 4i root 3. Same thing, same thing. And so what we'd have here is 32 plus or minus 4i root 3 all over 8. The last thing to do is to say, okay, of my coefficients, of my 32, of my 4, and my 8, can I simplify those in any way? They can all be divided by 4. So I'm going to divide the numerator by 4. I'm going to divide the denominator by 4. 32 divided by 4 is 8, plus or minus I root 3 all over 2. Now, that is how I prefer that these things are kept. If you do this on Desmos, they will sometimes divide this 2 straight through, and they'll say 8 divided by 2 is 4, plus or minus I divided by 2, that's 1/2 I root 3. That's how you'll see it on Desmos. I think this looks a lot nicer. So that's it for today. Good luck with this one, and welcome to imaginary, right? Imaginary numbers, and sorry, I forgot to highlight this part. Complex just means part real, part imaginary, and that's what 8 plus or minus I root 3 would be.